Hi, Anirban.
Okay, I'm on mute. Hi, Venkatesh.
You can see my screen, right?
Yes. You just want to try the slide transitions just in case?
Sure.
Sounds good. Sounds good.
Hello.
Yes.
I guess someone was speaking and I could not hear properly. So I was wondering if the issue was on my side.
So, organizers, do we start exactly at 2 or do we give some slack time? You could let me know. So, and I sort of start the intro.
We can start exactly at 2.
Sounds good. Thank you. So, shall we? Okay. So it's my sounds good. So it's my distinct pleasure to introduce Pranit Natrapalli. Welcome to the session of the RDA, and we're looking forward to exciting talks throughout the session. And it's my distinct pleasure to introduce Pranit Natrapalli. And I'll just keep it short because there's a lot to talk about. Pranit is currently a research scientist at Google Research India and an adjunct professor at TIFR, as well as a faculty associate of ICPS, right? And so he's had a long and distinguished career while being at Microsoft Research India, as well as UT Austin and Goldman Sachs. He has done quite a lot of very interesting work in designing robust machine learning algorithms, right, as well as other black box optimization techniques, as well as he's also been awarded for a lot of this. And over to you, Pranit. Looking forward to hear from you. I'm very excited.
Thank you, Anirban, and firstly, thanks to the organizers for organizing this workshop and also inviting me. I want to talk about a couple of different aspects of like there are several algorithmic aspects in stochastic optimization that we have worked on in the recent past, and over the two talks I want to discuss two of them, and the ideas, at least like the fundamental technical ideas, have a lot in common. So I hope that the first talk can serve as kind of a primer in understanding how these things are analyzed, and in the second talk I'll use this to kind of describe also like another new algorithmic idea that we came up with recently and it seems quite interesting to us. Okay, so yeah, was there a question? Okay, So this is joint work with many wonderful collaborators, and the one that I'm going to be talking today about is joint work with Prateek Jain, Shyam Kakade, Rahul Kidambi, and Aaron Sexton.
I request everybody to please be on mute. Thank you.
Okay. So let me begin with an overview. So as all of us are perhaps aware of, optimization is a big part of large-scale machine learning, and stochastic gradient descent is the workhorse in most of the practical applications. And while stochastic gradient descent is very widely used and has been observed to have very good empirical performance, there are several aspects of SGD that are important for its good practical performance. And some of the examples include what is the size of mini batch that we use in running SGD, and how can we distribute SGD to work over multiple machines, and how do we do acceleration, which is a optimization technique to speed up convergence, and what is the kind of learning rate schedule that we use as time progresses. And similarly, uh, what do we do when we are encountered not with independent data but dependent data, such as the ones that arise in, say, time series analysis or reinforcement learning and so on. Okay. So as I mentioned, like while SGD is widely used and has been observed to have very good performance, these aspects and how exactly each of these is tuned is actually quite important for its good practical performance. So our work has been to do a thorough investigation of all of these aspects, particularly for linear regression and also beyond linear regression, at least in some settings theoretically and in several settings also empirically. Okay. So in this talk, I'll particularly be talking about two aspects. So in the first talk, which is today, I'll be talking about acceleration and how we can extend what does acceleration mean in stochastic gradient descent, and how do we extend acceleration from deterministic optimization to stochastic optimization. And in the second talk tomorrow, I'll be talking more about how do we learn with dependent data. And the reason I'm talking about like two different things is that the underlying analysis tools and techniques are quite related, and they share a lot of the underlying ideas. So today I'll be talking about like the first thing, which is acceleration, and tomorrow I'll be talking about learning with dependent data. Okay. And again, so if there is any question at any point of time, please feel free to stop me. I'll be happy to answer questions right away. So let me begin with like a brief introduction of optimization. So one of the most fundamental and classical algorithms for optimization is gradient descent and goes all the way back to Cauchy. And the idea is that if you would like to minimize a function f over a parameter space w, then gradient descent looks at what is the direction in which the function decreases the most if I were to move like unit direction. And the next iterate wt plus 1 is nothing but w2 minus a delta step size, which is called the step size delta, times the gradient direction. Okay, so this is gradient descent, and it's classical and of course like very well known. And we'll also be particularly looking at the problem of linear regression, where the function f is given by the following equation, where we have a matrix X, each row of X transpose is called a sample, and we have a column vector Y, and each element of Y is called an observation. So our problem would be that we want to find a W which minimizes the L2 norm square of X transpose W minus Y. Okay. And this is, of course, a very fundamental problem and arises pervasively in applications. So this is deeply studied in literature because in addition to its importance as a standalone problem, it's also used as a subroutine in many other problem settings as well. And that's the reason why this problem has been studied so deeply. So one of the first questions that we'll ask ourselves in this context is, what if we apply gradient descent to solve linear regression, then what is the guarantee that we can get, right? And in this case, firstly, the update takes the following simple form, where the gradient can be computed in this form. So we have x times x transpose w2 minus b. So x transpose, so this should actually be the same as y. Sorry for the typo. Yeah, so x transpose wt minus y, b or y. So this thing is basically the residual, and we are combining the columns of x according to their residuals, and then we move in the negative gradient direction. Which is what gradient descent does. So in order to state the performance guarantee of gradient descent for linear regression, we need to introduce a little bit of notation. So let f star be the minimizing value of the function f. Okay, and then we define the condition number of this problem as the ratio of the smallest to largest singular value of the matrix XX transpose. Okay, you look at the matrix XX transpose and we look at the ratio of the largest to the smallest singular value, and this is called the condition number. And if our goal is to find a W such that f of W minus f star is less than or equal to epsilon, right? Convergence rate basically means the number of iterations of gradient descent that is required in order to find a W which satisfies this condition. Okay, and it is well known that gradient descent requires a number of iterations which scales linearly in the condition number. So it's kappa times a logarithmic factor that depends on the initial suboptimality f of W0 minus f star divided by the final target suboptimality epsilon. Okay. So the important point here is that the convergence rate scales linearly in the condition number. Any question? Okay. So a natural question is whether it's possible to do better than gradient descent in terms of this convergence rate. And the hope is that gradient descent actually does not reuse past gradients, right? It only looks at the gradient at WT. And when it goes to WT plus 1, it no longer looks at all the past gradients. And the hope is that somehow maybe we can reuse past gradients to actually do better. And the answer actually turns out to be yes. And there have been several celebrated algorithms, including conjugate gradient, heavy ball method, accelerated gradient, and so on, which actually improve the convergence rate of gradient descent for different classes of problems. Okay, and these algorithms all share, like at a fundamental level, they all have some similarity, and consequently, all of these methods together are known as momentum methods. So let me explain how one of these methods, in particular, like the Nestrov's accelerated gradient method, looks like compared to the gradient descent algorithm. Okay, so in Nestrov's accelerated gradient, we have two iterates, WT and VT, whereas in gradient descent, we only had one iterate, right? And also, there are two kinds of steps. From VT, we take gradient steps, and this gives us WT plus 1. And from WT plus 1, we take a momentum step, which is basically, we look at how WT has changed to WT plus 1. So we want to shoot further in this direction, and this is called a momentum step, and this gives us VT plus 1. Okay, so in the notation that we just established in the previous slide, where f star stands for the minimum value of f, and kappa stands for the condition number of XX transpose, right? The convergence rate of Nestrov's accelerated gradient descent turns out to be a square root of condition number times the logarithmic factor, whereas for gradient descent, it was linear in condition number, right? Yeah. So so in terms of equations, the algorithms again looks very similar to gradient descent, where the per step computation, right? So where WT plus 1 is being updated as VT minus the delta times the gradient of VT, and VT plus 1 is WT plus 1 plus like the momentum factor from WT plus 1 to WT, right? So so in terms of per step computation, all we are doing is we are just computing one gradient. And is there a question? Okay. So yeah, so in terms of per step computation, all I was trying to say was that the order of the per step computation is the same for both Nestrov's accelerated gradient as well as gradient descent. However, the number of iterations taken is much smaller for Nestrov's accelerated gradient, where it is square root kappa compared to kappa for the gradient descent algorithm. So note that this is a ratio of max over min, so this is always greater than or equal to 1. So square root kappa is indeed less than or equal to kappa, right? And right, this is what I was trying to say. And it's not just a theoretical improvement, even on like moderate condition number problems. In this case, for example, where the condition number is of the order of 100, we can see that accelerated gradient descent is actually an order of magnitude faster compared to gradient descent. So accelerated gradient descent is widely used in practice in several applications involving not only linear regression problems, but also other convex optimization problems.
One question.
So, yeah.
So are there some assumptions on F in these momentum based methods?
Yeah. So this guarantee can be proved for any function f which is smooth and convex. What is meant by smooth is that roughly you can think that the Hessian you can replace this condition number to be condition number of the Hessian at a point, and then you want to say that the maximum condition number of the Hessian at any point in the space is bounded by kappa. Then you get this kind of guarantee. Does it make sense?
But no extra guarantees compared to gradient descent convergence rates.
What do you mean by no extra guarantee? So gradient descent can only get a kappa, whereas here we are getting a square root kappa.
Yeah, but there also you need these assumptions like convexity.
Right. So, I mean, beyond convexity, it's hard to really say a lot of things. So there is work which tries to identify rates of convergence to local minima or even like stationary points, where you define optimality not as like closeness to minimizer, but maybe norm of the gradient or whether the Hessian is almost positive, semi-definite, and so on. So even in those cases, we have been able to show that Nestrov's accelerated gradient can get improved convergence compared to gradient descent, but the convergence is not to global minima.
Yeah, thanks.
Hey, Pranit, so you've written theta in the convergence rate. Is that to suggest that there are functions for which you do need these many iterations?
That's correct. Yeah. Yeah.
Okay.
Actually, yeah. And even this one is actually theta in the sense that you can design problems for which it cannot be better than, for any given value of kappa, you can design a problem for which, yeah.
And how do you pick those delta gamma terms, or any sufficiently small step size?
So you have to choose them carefully. You have to choose them carefully, which depends on like the problem parameters, like the condition number, and gamma also depends on. Yeah, so there are two parameters that will be used to determine delta and gamma. One is the condition number. The other one is the value of the sigma max. So these are the two parameters that will be required.
And you don't change them with time. It's fixed.
So, gamma, yeah. So if you only care about, so there are two kinds of algorithms. One is anytime algorithm. There you don't want to fix t a priori. So you want to say that I just want to keep running the algorithm, and if I query it at any point t, I should get a point which satisfies some guarantee depending on t, right?
Right.
So there you would vary like gamma with respect to t. Delta will not change, but gamma will change. But in the other case, you fix a priori that I'm going to run it for like 1,000 or 10,000 or whatever, like some number of steps. Then you don't have to vary it with t. You can use a constant.
Got it.
Okay. Sounds good. So this was all like a primer more on standard optimization. So let me come in particular to optimization the way it's usually done in machine learning, which also leads us to the stochastic optimization problem. So the basic setting is that we observe n samples, so x1, y1 all the way up to xn, yn. All of these are drawn from some distribution of RD cross R. And we again want to minimize this function f hat, which is given by 1 over n summation over I xi transpose w minus yi whole square. Okay. While we are given these n samples, our actual goal is not necessarily to minimize f hat, but rather to minimize the function which is of the same form, the linear regression problem, but where xy are actually drawn from the distribution, and then we take an expectation over this quantity, right? So the difference between these two is that this is called the population version, where you're actually writing out the expectation. And this is called the empirical version, where you draw samples from the distribution and try to hope that this approximates this function, right? And if you want to directly solve this, gradient descent is not directly applicable, because you would, like, the gradient would again be written as expectations, and we cannot compute exact expectations, right? So people have studied this in the context of stochastic approximation. Again, has a very long history, going back 60 or 70 years. And let me now explain what this, so what people have, like what is the algorithm that people have developed in this context, where we are getting samples and not expectations from the underlying distribution. So the original algorithm goes back to Robinson Monroe, and that's a paper which actually first introduced stochastic gradient descent. And the main idea is that instead of computing the gradient of f, you replace it with grad hat f, where grad hat f is actually computed just using a single sample xt comma yt. Okay. The nice property of grad hat f is that the expectation, when you take expectation over xt comma yt, is equal to the gradient of f at wt. And eventually, what do we return? So it turns out that instead of returning the final quantity, because this is a stochastic algorithm, it turns out that it's better to actually return some kind of average. And we can return something called a tail average, where we average over the last so many iterations and then return that as the final solution, right? And for linear regression, SGD is particularly popular because it takes the very simple form where, given a sample xt comma yt, you just compute xt transpose wt minus yt times xt. So this requires only one matrix vector product, and then this again like a linear vector operation, right? And one of the reasons for its popularity is that it's actually a streaming algorithm where you look at one sample, you take an update, and then you move on to the next sample and so on. And this is the reason why it's widely used in practice. Okay. Right. So just like we could change gradient descent to stochastic gradient descent, we can ask whether we can convert these momentum algorithms also to their stochastic counterparts, where we don't have access to exact gradients, but we only have these access to stochastic gradients, right? So you can easily like replace the gradients with stochastic gradients, and then with heavy ball you get a stochastic heavy ball method. With Nastrov's accelerated gradient, you again get stochastic Nastrov's accelerated gradient method, right? And the question is like, what can we say first about the convergence rate of stochastic gradient descent, and also about the stochastic momentum methods, right? So let's first look at the convergence rate of stochastic gradient descent, and in particular, let's also consider the special case where there is no noise, meaning that there exists a true W star, so that Y is exactly equal to X transpose W star. Okay. Using similar arguments as in the gradient descent convergence rate, we can argue that the convergence rate is again linear in the condition number, actually slightly different, but which basically goes like the denominator is exactly the same, which is the smallest singular value of a singular value. It turns we can replace it with the maximum norm of x square. Okay. So this is the notion of condition number. It turns out that this is the right notion of condition number for the stochastic setting. And the convergence rate again is this linear in condition number times a logarithmic factor that depends on the initial and targets of optimalities. And finally, in the noisy case where Y is actually equal to X transpose W star plus some zero mean additive noise, there is an additive term in this convergence rate which depends on the variance of the noise, which is sigma square, which is defined as expected value of n square. Okay. Any question about the convergence rate of SGD? Okay. Okay, so let's summarize like what we had known until
question,
like our work. Yeah, yeah.
So this notion of condition number that you said, any short intuition you could give us? Why is that the right notion? Because the numerator looked a little strange. Why is that the right notion of condition number?
So you can think of it this way. So every time, okay, so in earlier the gradient descent, so Wt was being multiplied by XX transpose. I'm not sure if you remember. Right. So the gradient has Wt was being multiplied by XX transpose, right? And what comes here is actually the maximum singular value of whatever is being multiplied here. Okay. So in order to ensure that it's kind of stable, so like you'll require step size to be smaller than. So if this quantity is large, then delta has to be small, and that's why it enters into the convergence rate, right? So here it's the maximum singular value of this XX transpose that was appearing here. So in this case, if you look at the term that's sitting Wt, it's actually XT transpose, right? So if you look at the norm of this XT rank 1 XT transpose matrix, that's nothing but the norm of X square, norm of X square. So that's yeah. So that's the reason you'll be you'll be forced to choose a step which is small compared to the XT square. Okay. Okay. So.
Hey, quick question, Praneeth. Yeah, before you go. So this max is over the samples, like so it's max over
support,
T.
yeah, over the support of the distribution. Yeah.
And is it that fragile, as in can't like?
Yeah, so you can replace it with a fourth moment kind of quantity.
Okay.
So, but I did not want to.
Fine. Yes.
Make the notation
right.
more cumbersome.
No. Thanks.
Yeah. Yeah, but you can replace it with some fourth moment related quantity. Okay, sounds good. Sounds good. So, is there a delay? Hello?
Your voice is a little choppy
Okay, so let me
sometimes.
maybe continue. If there is any issue, okay. Okay, so let me try. If there is an issue with hearing me properly, please let me know. I'll try to do something. Okay, so just to summarize, like the current situation, like all the results that we have seen so far. So in the deterministic case, we have seen that gradient descent has a convergence rate which depends linearly on the condition number, and momentum methods such as Nestrov's accelerated gradient descent were able to improve the condition number dependence to a square root of condition number, right? And in the stochastic setting, where we were only processing one sample per step, we saw that stochastic gradient descent again has a linear dependence on condition number. And the question we were asking was whether we can accelerate stochastic gradient descent even in the stochastic setting. Is the question clear? Hello?
Yeah, it's clear. Right, yeah.
Okay, sounds thanks. Sorry, I was just pinging just to make sure that I have not lost connection and I'm just going on and on and so on. Yeah. Okay, sounds good. So this is the main question that we would like to understand. And it turns out that the second quantity that we have here, it's actually indeed optimal statistically. So information theoretically, we cannot do better than this. So the question is, can we actually improve the first term that's appearing in this bound? Okay. And first, let me convince you that this is actually important, because in most of the implementations of SGD, even like when we are trying to use them to solve like train neural networks and so on, uh, the algorithms that are currently available actually use a stochastic variant of Nestrov's accelerated gradient descent. And while in the deterministic setting, we have seen that it can actually give orders of magnitude improvement both in theory and in practice. It turns out that theoretically there has been no prior work which tries to understand whether momentum can actually improve convergence rate even in the stochastic setting. Okay, and there have been some papers which try to investigate the effect of momentum in the stochastic setting, but it's not in the machine learning setting where we are getting samples one at a time and so on. And I'll be happy to discuss offline about like the difference in the stochastic models that are used in the prior work compared to the ones that we are more interested in studying. Okay. So the bottom line is that the first term can actually be improved to something better. And let me first give you an outline of our result. So the first result is actually an impossibility result, which says that you cannot always improve the condition number dependence to a square root of condition number. So this is actually a negative result. But at the same time, we would like to understand whether improvement is ever possible. And then we are able to show that there are some settings where improvement is indeed possible. So the third question is whether existing algorithms such as the stochastic variants of these heavy ball and Nestrov's accelerated gradient, whether they can actually achieve this improvement. And it turns out that they cannot, and in fact, they are no better than stochastic gradient descent. And finally, we are able to design a new algorithm called accelerated stochastic gradient descent, which can probably improve the condition number dependence to something better whenever information theoretically it is possible. Okay. So let me run you through each of these briefly before I go into a bit more detail on the final part. Okay. So the first question was whether acceleration is always possible, and let us give like a counterexample to argue that it is indeed possible. So let's consider the noiseless setting where y is exactly equal to x transpose w star, and we have already seen that the SGD convergence rate is linear in the condition number. Okay, and we are hoping that whether an accelerated rate of say square root condition number is indeed possible, right? So there is no second term because this is noiseless, and second term just disappears. So the example that we would like to look at is a discrete distribution where x is just 1, 0 with like very high probability and 0, 1 with very low probability. Okay, and in this case, we can indeed compute the condition number, which turns out to be 10 to the 4, because the norm of x square is equal to 1 with probability 1, right? And when it comes to the Hessian, it is diagonal with elements 0.999 and 0.001. So the smallest single value of the Hessian is just 0.0001. And so the condition is to the 4. And the question we are asking is whether a convergence rate of square root condition number times logarithmic factor is possible. And it turns out that so this is equivalent to at least either version of this is asking whether we count the error using a square root condition number or 100 samples, right? And what we first observe is that if you have fewer than 100 samples, it means that we do not observe this element at all, which means that we cannot compute. So because this is a second basis vector, we cannot estimate the second component of W star at all. Okay. What this shows us is that we can actually do no better than linear dependence on condition number. So in particular, acceleration is not possible for this distribution, and so it's not possible in general. Okay. So we cannot always improve the linear dependence on condition number to a square root condition number. So any questions about this or this example?
So just a quick comment. So then, is it true that here you're assuming that the definition SGD, which is a definition, is that the samples are chosen uniformly at random. If there's some non-uniform distribution, then this example does not hold. Am I correct in thinking about that?
That's correct. So what we want to say is that whether you can improve the dependence from condition number to square root condition number. So you cannot always hope for an improvement. So you cannot design an algorithm which always does this improvement, because there are some cases where this improvement is not possible information theoretically. So
I wanted to say is that if HGD is somehow choosing samples non-uniformly, then this example doesn't rule that out, right?
Right. So here SGD is actually okay. So the setting that we are in is that you only have access to uniform samples from the given distribution. So you are in the streaming setting where this is the only access you have, and this is like an information theoretic argument that no algorithm can work in this setting. Right. So let's now look at a different example, which is the Gaussian distribution, where the Hessian is again the same as in the previous example, 0.9999 and 0.0001. However, in this case, so even though the condition number is again like 10 to the 4, because we see that the vectors are always of unit norm with high probability or like constant norm, and the smallest singular value of the Hessian is still 0.0001. So the condition is again 10 to the 4. However, even when we get two samples, just because of the properties of Gaussian distribution, we know that the empirical covariance matrix xi transpose is actually invertible, right? So we can actually invert this matrix to find W star. So it is indeed possible to find W star just after two samples, which is much smaller than the condition number 10 to the 4, right? So at least information theoretically, acceleration might be possible for this distribution. So again, like even here, we are getting only uniform samples from the distribution, but the distribution here is Gaussian. So the answer to the second question is that acceleration might be possible under some settings, but it does depend on other problem parameters, right? So when we dig deeper on what is the information theoretic quantity that can help us achieve faster convergence of the underlying parameter, we see that the key difference between the previous and this setting is that the empirical covariance matrix here concentrates much better so we have much better spectral concentration of the empirical covariance matrix to the true covariance matrix as compared to the previous example. And one of the key quantities that tells us how fast this spectral concentration happens is called matrix variance. Okay, so let me be a bit more concrete. So let's say we have this xi coming from a distribution D, and let's say H is the expected covariance matrix of xi, right? And what we want to argue is that we want to say that we want to find a number of samples n such that the empirical covariance matrix is close to the true covariance matrix H. Okay, and the question is how many samples n are required in order to guarantee this. If xi was just a scalar, we know that variance gives us a good quantity, or in general, like maybe higher moments if you want high probability guarantees, right? So so variance, which is the variance of this x square quantity, is basically what tells us how many samples we need to collect in order for the empirical average to be close to the true average. And in the context of matrices, there is a similar quantity called matrix variance, and we call this the statistical condition number, which I'll describe next. So the statistical condition number can be defined as follows. So let's say H is the covariance matrix, the expected covariance matrix of xi transpose, right? So we look at say a given direction E, right? And so on that particular direction, the condition number is more like what is the average value of xi in this direction. So we look at the norm of E transpose xi whole square divided by the expected value that this quantity takes, okay, for any given vector E, and then we sum it across all the different eigendirection basis of the matrix H. Okay. So this basically tells us that we can have larger norm in some directions, but it's just that the corresponding, as long as the corresponding expected value is also large, then we'll be able to approximate that direction fairly quickly. So this is what is called the statistical condition number. On the other hand, what we are calling the computational condition number is actually taking a summation over the numerator, but replacing the denominator by a minimum over all directions E. This is what gives us the minimum eigenvector of the Hessian matrix. So in this sense, so once we pose it like this, it's clear that the statistical condition number is actually smaller than the computational condition number always. And our previous matrix concentration example suggests us that acceleration might be possible if the statistical condition number is much smaller than the condition number kappa. Okay. So any questions on this one? Okay. Okay, so let's compute the statistical condition number versus the computational condition number for the discrete as well as the Gaussian distributions that we saw earlier. So for the discrete distribution, it turns out that the statistical condition number is still of the order of 10 to the 4, which is the same as the computational condition number. Whereas for the Gaussian distribution, it turns out that the statistical condition number is only about 100 compared to 10 to the 4 in the computational of the 10 to the 4, which is the computational condition number. So in this case, the statistical condition number is much smaller than the computational condition number, and we would expect acceleration to be at least information theoretically feasible in this setting, whereas it may not be feasible at all in this setting. Okay. And so just to give an illustration of how these SGD behaves on these two different settings. So the left plot is the behavior of SGD for the discrete distribution, and the right one is for the Gaussian distribution. The green curve plots the error versus the number of iterations. Okay, and the pink dotted line indicates the statistical condition number on the x-axis in both the plots. Okay, so here it's of the order of 10 to the 4, whereas here it's of the order of 100, and we can see that the geometric decay, or like the sharp decay, starts pretty much about the computational condition number for the discrete setting. And even for the Gaussian setting, even though statistical condition number is much smaller, the drop again seems to happen pretty much at the same point, right? What this suggests is that even though information theoretically it may be possible to achieve a faster convergence rate, SGD itself is not achieving that faster convergence rate, and the sharp decay is still happening on the at around like the 10 to the 4 samples, which is the value of the computational condition number. Okay, so given that SGD is not achieving acceleration even when it is possible, the next question we wanted to ask was whether existing algorithms such as like stochastic momentum methods, can they achieve this improvement? And it turns out that the answer is again no, and we are able to construct distributions where the statistical condition number is actually much smaller than the computational condition number, but the rate of stochastic heavy ball method is no better than a linear dependence on the condition number. Okay, and the same statement actually seems true even for empirically, it seems true even for Nestrov's accelerated gradient descent. However, we have not been able to prove this statement for the accelerated gradient algorithm. And I should also mention that the distributions that we construct here are fairly natural, not very bad cooked up, not like very badly cooked up distributions, but rather seem fairly natural. And the point is that the stochastic versions of existing algorithms do not really seem to provide an improvement over stochastic gradient descent, even for these reasonably benign distributions. Okay. Right. So as we can see from this plot, the behavior of empirical behavior of both stochastic heavy ball and Nestrov's accelerated gradient is not much better than that of stochastic gradient descent. So let's now come to the final question that we were asking, which is whether we can design an algorithm which can improve over stochastic gradient descent and achieve acceleration whenever it is possible. And the answer is yes. And it turns out that we can, so we are able to design an algorithm that we call accelerated stochastic gradient descent, which improves the dependence of on condition number kappa to be a square root of kappa times kappa twiddle. Okay? Because we have already shown that kappa twiddle is always less than or equal to kappa. This number is always an improvement over the condition number. And in cases where kappa twiddle is much smaller than kappa, this can be much smaller compared to kappa. So is the bound clear? Any question about the result?
So quick question. So like this, the statistical condition number is smaller, but is there still a complementary bound saying that it'll be, let's say, the dimension times kappa, or can the ratio be really large, like unbounded? So probably
the ratio can actually be, yeah. So the ratio can actually be unbounded. So for example, if you take the Gaussian distribution, kappa twiddle will always be equal to the dimension, and kappa can be arbitrarily large.
By skewing the Hessian, like just picking a
by
very
skewing
small...
the Hessian. That's correct.
Okay.
That's correct.
Right.
So kappa twiddle for Gaussians is always equal to dimension. Yeah.
Okay.
Okay. Yeah. Thanks
And
for
you
the question.
don't need the... So it's not like the a priori knowledge of these condition numbers that matters. It's just that like the standard stochastic gradient isn't able to leverage this.
That's correct. Right. Right. So, I mean, even in our algorithm, at least to set the parameters and everything, we need the knowledge of kappa twiddle and kappa. But even if you give that kind of knowledge, it's just that SGD is not able to do the right updates. So it's more about the form of the updates rather than the knowledge of these parameters.
So, okay, yeah, maybe like final question. So, like, why is SGD not doing well for the Gaussian? So I'm just wondering that plot, is there some intuition to understand like the waterfall diagram that you showed in one of the previous slides, that even for the Gaussian case where this kappa tilde is fixed constant, SGD actually has a really long warm-up period before it starts dropping.
Right.
So why?
So again, yeah. So the main reason, I mean, the main reason again comes from the deterministic setting. So even in the deterministic setting, for example, there is no statistical aspect there, right? And even there, gradient descent is not able to improve because it cannot choose a very large step size because you will diverge in the larger eigendirection. And if you choose a smaller step size, then your progress in the smaller direction will always be limited. And that's the same reason even in this setting. And accelerated gradient descent, somehow it's able to use updates which kind of simultaneously do faster progress in the lower eigendirections without really blowing up in the larger eigendirections. And somehow like the key idea is how to do this in the stochastic setting. So for those of you maybe who are familiar with like Chebyshev polynomials, the improvement from kappa to square root kappa, at least in the deterministic setting, is again like related to the fact that so Chebyshev, right. So if you want to go from 0 to 1 in a very small interval delta while being bounded in the domain 0 to 1, then the degree of the polynomial required is of the order 1 over square root delta. So it basically follows from the same thing. Basically that you want to design a polynomial which does not blow up in the larger eigendirections and at the same time it also has faster, like it's close to zero in all the in the entire eigen space, right? So yeah.
So it's this balancing act that kind of forces the
Right. So SGD is doing the like naive polynomial, whereas Nestrov's accelerated gradient is taking advantage of the fact that you can design better polynomials, like lower degree polynomials, which can still do this. Yeah.
Correct. Thanks.
Yeah. Right. So yeah, before I go into the like ideas of the proof and so on, so let me just show the empirical evaluation of these algorithms. So again, like the green thing is the stochastic gradient descent. The black and blue, which are pretty much overlapping, are the stochastic versions of Hibby-Ball and Nestrov's accelerated gradient, which are currently implemented. And this red one is the algorithm that we developed. And we can see that there is at least an order of magnitude improvement in terms of the convergence rate compared to both stochastic gradient descent and the stochastic versions of these prior algorithms. And we also note that there is still a significant amount of gap between like the lower bound, which is kappa twiddle. This is the information theoretic lower bound, and the convergence rate of our algorithm. And so while we do not have a lower bound better than kappa twiddle, we believe that doing anything better than the square root of kappa twiddle might not be possible once you account for computational restrictions. So yeah, but again, like we do not have a proof for this statement. So let me describe the algorithm in a bit more detail. Yeah.
Yeah. So let me just ask one question. So for the specific case of the Gaussian, you can do better, right? You can just estimate the Hessian and then.
Right. So I guess what I'm saying is for a streaming stochastic algorithm,
Right.
so in particular, you can maintain memory only linear in D. Maintaining the Hessian will require you to have memory D square.
Right.
So if you're allowed memory only D, like all the algorithms that we know of are of this flavor, and we do not know how to improve over something like this. Yeah.
Got it.
Yeah. Thanks, Siddharth, for the questions. So let me, in the remaining like 10 to 15 minutes, so let me briefly describe the algorithm and the main ideas behind the proof. So it turns out that there are several equivalent versions of Nestrov's accelerated gradient in the deterministic setting, and we write the algorithm in different ways depending on different intuitions, like whether we look at it as a primal dual algorithm, or whether we have a slightly modified potential function that it's doing, or whether we look at it as a discretization of Newton's equations of motion, right? So there are different ways of looking at Nestrov's accelerated gradient descent, and depending on which way you look at it, you can parameterize the algorithm in different ways. And in particular, like there is one formulation which has both an upper and lower bound interpretation, which is much less popular in terms of like the way it's implemented, because as you can imagine, like a 2-iterate version is much more compact to write, whereas the 4-iterate version is much more elaborate. But it turns out that this 4-iterate version actually captures the essence of what we want to do in the stochastic setting. So the idea is the following. So right. So we have 4 different iterates: U, V, W, and Z. And what we are doing is we are doing gradient descents at some points. So for example, Vt minus 1 is a gradient descent at Wt minus 1, but using gradient at a different point. Okay. So we do gradient descents starting from one point, but using gradients of a different point. Okay. Sorry. So sorry, I misspoke. Okay. So we have 2 different endpoints, U0 and U and Z, and we take a point Vt minus 1, which is on the line between U and Z. And then we do a gradient descent at Vt minus 1 that gives us the next iterate Wt. And similarly, we do a gradient descent at a different point Zt minus 1, but we use gradients of Vt minus 1 again to get a new point Ut. Okay. So the algorithm is slightly complicated. And maybe it's difficult to explain the intuition behind this in the short talk, but let me go to the proof and try to expand how to explain how to where some of these aspects come from. So So we recall our guarantee that we can replace the linear dependence on condition number with the square root of condition number times the statistical condition number. And as we saw, the first term actually depends on initial error, and the second one is the statistical error, right? And we can actually do two different analysis for the two terms. And for the first term, we can just analyze the problem assuming that there is no noise and sigma equal to 0. For the second term, we analyze assuming that W0 is equal to W star, so that this term disappears and only the second term remains. Okay. So for the first part, we actually use a potential function, which is pretty much inspired by the deterministic analysis of the deterministic version of accelerated gradient descent that I described here. So the main idea is that use a potential function where you track the distance between Wt and W star in the Hessian norm. And at the same time, you track the distance between Vt and W star in the L2 square norm. Okay. From a intuitive point of view, what this is trying to do is this is the function value difference. So this is like the primal bound, and this is the dual bound because we'll always be using gradients at Vt, and gradients at Vt certify a lower bound on the function value. Okay, so the potential function is a combination of a primal value and then also a dual value. So this is indeed a primal dual method, and the key change that we do in the stochastic setting is that when we look at the H here, it turns out that the so the bounds that we get are much worse. So in order to deal with that, what we do is that we observe that we can actually, so as long as we fix the eigenbasis of H, right? So we can think of H as a diagonal matrix. It's just that we are using different weights for different coordinates here, whereas we are using the same weight for all the coordinates here. We can actually shift the weights in the same way in both of these terms. So when we multiply this with H inverse on both the sides, we get a L2 square norm here and a H inverse square norm here. Okay. And once we do this, it turns out that the guarantee, so we can convert the same analysis in the deterministic setting, where the convergence rate can now be bounded by 1 minus 1 over square root of kappa kappa twiddle. And this is what gives us the square root of kappa kappa twiddle convergence rate in the first term. Okay. Now, the more challenging part was the second part, where we want to analyze the effect of noise. Okay. So in this case, we assume that we are actually, let's say, at W star, and what is the effect of noise. So in order to do this, we look at the following update. So where Wt plus 1, so let's first look at the, yeah, so we look at Wt plus 1 minus W star and Vt plus 1 minus V star, W star, right? We can actually, because everything is linear here, we can actually write this as a linear process where we have a matrix C multiplying Wt minus W star, Vt minus W star plus some noise. And when we write Tt, when we do not using theta t, the covariance matrix of at time t, right? We can again write this like multiply this with its transpose, and then we get again a linear equation for theta t plus 1, which is an operator b times theta t plus noise transpose. Okay, so when we expand this all the way till 0, we see that the final covariance matrix theta n can be written as a power series summation over I b to the I times noise transpose. And because the noise is identical across different time steps, we can replace this with I minus b inverse, where b is this operator. Okay. So the bottom line is that we need to understand this I minus b inverse times noise transpose. And the key challenge in understanding this is that b turns out to be an asymmetric matrix and consequently has singular values which are greater than 1. But however, it turns out that it has eigenvalues smaller than 1. So I minus b inverse indeed is well defined, but we are not able to do naive bounds just using the singular decomposition of b, right? And the way we do it is to solve the one-dimensional version of this I minus b inverse times noise transpose using explicit computations. So when b is one-dimensional, and so we do this in every eigendirection corresponding to the Hessian. And once we have this one-dimensional version of this bound, we can combine all these one-dimensional bounds using the statistical condition number bounds. And finally, what we get is that the expected value of W minus W star, like the at any iterate t as t goes to infinity, is upper bounded by kappa twiddle H inverse plus delta times identity. So delta is the step size and kappa twiddle is the statistical condition number, and H is the Hessian of the problem. Okay. Okay. So once we note that this is actually the final bound on the final variance of the final iterate, and in order to get a bound on the average iterate, this becomes a bit more complicated because instead of theta t plus 1, we want to understand the covariance matrix of the average iterate. But basically the same kind of arguments can again be applied to bound the average iterates covariance matrix, and that basically gives us a statistically optimal bound, which is sigma square d over n, while the bias decay rate, which was square root kappa kappa twiddle. So this was gotten using the analysis of the part 1 in the potential function. So any questions about the high level argument? Okay. So to summarize so far, so we have seen that for linear regression, we have completely theoretically understood like the behavior of various algorithms, including SGD, stochastic versions of AB ball, Nestlov's accelerated gradient, and then we also designed a new algorithm which improves over all of these algorithms. And the question is, in practice, beyond linear regression, what is and the one of the first questions that we wanted to understand is, why do stochastic heavy ball and Nestlov's accelerated gradient algorithms still work better than stochastic gradient descent in practice? And our major answer was that we are doing mini batching. And what mini batching does is that when we have a large enough sample in the mini batch, then the stochastic gradient is pretty much close to being the actual gradient. So this takes it closer to the deterministic setting, where we know that heavy ball and Nestlov's accelerated gradient are indeed giving can give provable advantage over stochastic gradient descent, right? And the precise quantification of small or large depends on the data set and on the problem parameters. And the key advantage of accelerated stochastic gradient descent is that it improves over stochastic gradient descent even for small mini batches. And yeah, so we have some empirical results which show the improvement. Maybe I'll skip this in the interest of time. Yeah, so let me just try to recap. So we saw that in the deterministic case, gradient descent has a linear dependence on condition number. Nestlov's accelerated gradient descent can improve this to a square root of condition number. In the stochastic setting, again, SGD has linear dependence on condition number. And we saw that naively replacing gradients with stochastic gradient descent no longer do not get any improvement over stochastic gradient descent in the stochastic setting. Whereas we were able to design a new accelerated stochastic gradient descent algorithm, which improves the kappa dependence to a square root of kappa kappa twiddle, where kappa twiddle is the statistical condition number. And whenever this is much smaller than kappa, this provides significant improvements. And in practice, this seems to work even beyond linear regression problems. So yeah, so that's all I wanted to say. Happy to answer any further questions.
Questions?
Praneeth, so the lower bound that's known in the stochastic setting is square root k tilde, or is it k tilde?
So again, like that's a good question. It would be kappa twiddle. It's not square root, and that's again. Let me put it this way: that's the tightest known bound known for matrix spectral concentration. What we can show a lower bound for is that if you don't have matrix spectral concentration, you will not be able to solve the problem, right? And this is the best known upper bound for matrix spectral concentration. There are also some lower bounds in some settings, but it's not a per problem kind of lower bound.
Okay.
Yeah.
So, I mean, I guess what I was trying to understand was like in settings where kappa and kappa tilde are equal or like very close to each other, this is like this accelerated.
This will not be useful. Yeah, this will not do anything better than stochastic gradient descent.
Okay.
Again, like I guess we don't have a lower bound proof like that, showing that it's going to be theta, but like I believe that it will not do better.
Sure. Yeah. Okay, makes sense.
Any other questions? I have one and ninth one possibly. That is it possible to sort of quickly see to get a sense of whether kappa tilde is much smaller than kappa for a given data set?
Actually, like for kappa twiddle, we give an explicit expression.
Okay.
So we can indeed compute it, and so it requires us to compute the Hessian, but it also involves like inverting the Hessian.
Okay.
But if you are able to do that, you can compute kappa twiddle for a given distribution.
I see. Any other questions? We still have a couple of minutes. Okay. If not, let's thank the speaker. I mean, everybody is still on mute, so I'll thank Praneeth for an excellent talk on behalf of everybody. Thank you. Thank you.
Thank you, Anirban.
So I'll request the next chair to the next person who's chairing to take over.
Yeah, sure. Thanks, Anirban. Just confirming with the organizers though, do we have a break right now?
Yeah, Neil, we are supposed to start at 3:15. So
Right.
Yeah.
Okay. So in that case, maybe of course I see that Diptarka is here already, or do you want to?
Yeah, so I am already here. So
Right. Hi.
So we will start in 15 minutes, right?
Yes, we will start in 15. Just in case you want to check if your screen share is fine, you are co-host, so you should be able to share your
Okay.
screen.
So am I already a co-host?
Yeah, I mean, unless you've joined from multiple accounts, you
Okay,
are.
so yeah, so I will join from another device.
Okay, all right. So then we'll wait for you to do that.
Yeah,
Okay.
so I joined from another device. I think I am also co-host there as well, right?
Yes. It seems like you
Yeah.
co-host from both your logins now. And so you should be able to share your screen.
Yeah, I can see that. I can actually share. Yeah, I think I can share. So yeah.
Yeah, I think it looked like that was briefly visible. So, okay, sounds good. I think, because we're slotted up to start at 3:15 p.m. I'll just request all the participants to please stay on, but grab a cup of coffee or take a walk or whatever. But please be back by 3:15, and we'll start then. And I'm looking forward. Thanks.
Hi.
Hi.
Screen.
So is this sort of an ensemble survey talk, or is it more directly based on a specific paper of yours?
Well, so this is combination of some of my works. Yes, but I don't think I'll be able to cover all of them, but I'll try to give as much as possible.
Of course, sure.
Yeah.
Makes sense, yeah.
Yeah, but I guess today mostly I will spend most of my time on introducing the problems. I don't think I'll be able to cover any technical details today. So at least that is not my plan. My plan is to cover all the technical details tomorrow.
Yeah, I think that's intuitive, makes sense. Um,
You didn't go for a walk or cup of coffee?
Hey, so Smita, are you asking me?
Yes.
No.
I went to the kitchen and got a cup of coffee. That's a walk.
You did both. Yeah, cool. I think I have overdosed on my coffee quota for the day. So
Yeah, the late afternoon tend to be a little I don't know, sleep inducing. No matter what I eat or I don't eat. Always feeling little low energy around 3 o'clock.
yeah, no, that's correct. I think post-lunch coffee is always welcome. Deeptak, are you joining from Singapore? Yeah, what time?
Yeah.
Okay.
Yeah, it's already like 5:45.
Okay, so a little later in the evening.
Yeah, but it is not that late.
Right. Yeah, still a good time. So we'll just start at 3:15, right?
Sorry, did you ask me something?
Yeah, Vikram, we'll just start at 3:15, yeah? So
Yeah, in a minute, yeah, sure.
yeah, okay, perfect. All right, thanks. All right, appears that it's practically time. So welcome back, everybody, to the final session of the first day of recent trends in algorithms. We've been off to a great start. And it's a pleasure to introduce all of you to our speaker for this session, Diptarka Chakrabarti, who is joining us from Singapore. He is he's currently at the National University of Singapore, and he did his PhD from the Indian Institute of Technology, Kanpur, IIT Kanpur. And after that, he spent a couple of years at Charles University in Prague, the Czech Republic, as a postdoc. And after that, he spent close to a year in Israel at the Weizmann Institute of Science. And his research interests are broadly in theoretical computer science, span a variety of different themes and different kinds of problems. So he looks at algorithms on large data sets, streaming algorithms, string matching algorithms, graph algorithms, and data structures. He's worked on problems like, I think, edit distance, for example, really a lot of fundamental work there. So today he's going to be talking about aggregating a data set from rankings to strings. We'll be surveying some of his recent work on this broad theme. So we're really looking forward to both of your talks, Diptarka. This is the first of a two-part journey that we will be undertaking with you. So thank you so much, and it's over to you.
Okay, thanks, Nidhara, for the nice introduction, and also thanks to all the organizers for organizing this beautiful workshop and also inviting me to speak here. Yeah, so as you can see, so the title of the talk is Aggregating a Dataset Ranking to Strings. So I will not focus on any of my particular research work, but rather I will combine 2-3 papers and try to give as much as details as possible. But what I am planning today is essentially introduce you to a set of problems and do not give any solution to them today. And most likely tomorrow I will give solution to some of them, at least the solution that I am aware of. So yeah, so this, as I mentioned, I mean, this talk will going to be like combination of 3 of my works. And so I should thank all my collaborators. First of all, Debarati Das, who is currently assistant professor at Penn State University, then Robi Krautkamar, who is a professor at Weizmann Institute of Science, then Kshitiz Gajjar. I can see that he is here as well. He is also attending, so he is postdoc at NUS, and then also Agastha Vibhuti Jha, who is currently a master student at EPFL. So let's now start with this talk. So although the title suggests that so this have this word rankings to strings, but when I introduce the problems, I will actually go in the reverse direction. So I will start with string and then I go to rankings. But when I provide the solutions, maybe then I will take this direct route from rankings to strings. Okay, so let's start with this fundamental notion of string similarity measure. So suppose we are given 2 files, 2 text files, and I want to compare them, how similar they are. Well, so there are several classical measures using which we can find the similarity, or you can say dissimilarity among these files. For example, one classical one is the Hamming distance, where so there are suppose 2 binary strings, both are like contents of say 2 files. And now I will look into the positions, the coordinates where they differ. For example, in this example here, you can see that there are 5 positions where these bits are different. So then the Hamming distance is defined to be 5 for this input. But it turns out that for some of the applications, although the Hamming distance is a very classical notion, for some of the applications, it could not capture the real similarity between strings. For example, let's now consider these two pieces of text. So suppose somebody asks me that, hey, Deeptarka, so how is your life at NUS? And then maybe somebody else asks me, I mean, hey, how is your life at NUS? So it looks that these two texts are very similar, but now if you compare, I mean, if you compute the Hamming distance, like coordinate-wise dissimilarity, then you will see that for the large chunk of this text, they are dissimilar. Of course, I mean, for Hamming distance to be well defined, I mean, both the strings has to be of the same length, but let's assume that they are of the same length. Maybe I can append, I mean, although in this example, you can see that second text is much shorter than the first one, but you can append with 0 to make them equal length. But now the still the problem is there that they are showing that almost everything is dissimilar, but it is not the case actually. So the Hamming distance will be very large for this example. But as I mentioned, that they are very similar things. So if you delete just this word, I mean, my name Deeptarka from here, so then they will be look exactly the same. And that is how that is perhaps the motivation behind defining the edit distance. So what is the edit distance between two pieces of text? So this counts the minimum number of edit operation. And this edit operations that varies with the application. But in the most standard model, I mean, what we consider as edit operations are like character insertion, character deletions, or character substitution. Okay, so this deletion and insertions are defined from what we have seen for Hamming distance, because Hamming distance is essentially just character substitution. Okay. So, but this is completely up to us. I mean, depending on the applications, I mean, one can also consider different other set of edit operation, like if there are some large set of text, you can maybe move a particular line completely, and that could be treated as just one single edit operation. Or also you can maybe reverse the block, and that also sometimes could be treated as a single edit operation. Okay, so but throughout this talk, I mean, I will use this standard set of operations. So basically deletion, insertion, and substitution. So now you can see that for this example, so these are small. Okay, so and both Hamming distance and edit distance, they are very classical notion, and there are lots of works on it. And it has several applications. So like file synchronization, for example, when you edit some files, say in the Dropbox or somewhere, and you push them in the cloud, then depending on like how much edits you make in the new file, that will has to be actually computed while you shrink this file to the cloud. And another application could be like in NLP. So for example, auto spell correction. So here you can see that so when I say correction, so one R is missing. So you can see that these days most of the editors can automatically correct them. So these are also another application of edit distance. Then in the pattern recognition, computational biology, database system, and many more. Yeah, so I will not go into the details of the applications in this talk because this is a theory talk. So the one question, fundamental question is like, how do you compute edit distance? I mean, given two strings, how efficiently I can find their edit distance? So most likely all of us know that, I mean, we have learned in our undergrad algorithm course that there is a classical dynamic programming algorithm which can be used to compute this edit distance in quadratic time. And also it turns out that it is almost optimal up to some complexity theoretic assumption. And there are lots of work on approximating the edit distance in better than quadratic time. So yeah, so I am not going to list down this work on how we can efficiently approximate the edit distance, because this talk is not about them. So rather this, actually in this talk, we will not even consider the computing edit distance between two strings, but we will deal with multiple strings and try to consider some of the problems that involves edit distance. So for our purpose, computing edit distance is very simple. I mean, as long as, because since now I am going to be talking about multiple string, so there with respect to multiple string, just quadratic time is just polytime, and it is like a very easy problem, computing edit distance. So yeah, but I just wanted to note this, that there are several work on computing edit distance and approximating them. Okay. So now let's talk about a classical big data problem, which is clustering. Suppose there are several text files, and now you want to partition them according to the similarity between the files. So in this slide, I mean, I tried to denote this similarity by this color, if I use different color. So the question is, can we partition them efficiently so that the similar string are in the same partition? So you can think this as some kind of text classification problem or text clustering. So here you can see that all the reddish files should be in the same cluster, then greenish files should be in the same cluster, purple, and then yellow. Okay. And again, I mean, this clustering problem with respect to both Hamming distance and edit distance find numerous applications. So now let me start with one of the very beautiful application, I would say. And yeah, so actually that is how my journey towards this set of problems begin. I mean, I was introduced with this problem, and then I start looking into the more theoretical question involved here. So this application is like DNA storage system. So now we are dealing with the big data, and there are huge amount data we have to store, and soon maybe our current technology will fall short in storing such a huge amount of data. And so that's why many people propose various different techniques or technologies to store such huge data, and one of them is using the synthetic DNA. So yeah,
Sorry.
so I'm not sorry. Okay. So yeah, so I am not going into details. I mean, like why DNA storage should be better than the magnetic tape system and all, because even I am not completely aware of all these details. But let me abstract out like what are the theoretical problems that we will get from there. So what happens in the DNA storage system? So we are given a data and we have to store them. And now there are several pre-processing involved before storing a data. So generally first, it has to be encoded in some sequence of alphabet, only A, C, G, T. So this 4-letter alphabet, and then people randomize that sequence using some of the pseudo-random sequence, then use some of the error correcting codes, and then finally whatever we get, that is stored in a synthetic DNA. Okay, that is synthesized in the synthetic DNA. And now, well, while actually they are synthesizing this DNA, so they are also divided into small chunks. And due to this pre-processing, since we already randomize it, you can see that different chunks the distance between them are pretty large. And here, when I talk about distance, I will always consider the edit distance. So it is not actually hard to show that for if you randomize a string, I mean like given two random strings with high probability, their edit distance will be large. So that's why now all these blocks, so their edit distance will be large. And that's why I use different color there. But now, I mean, this is fine, the storage part. Now the problem comes like, how do I access them? Because they are synthesized in some biological system, some DNA. Well, so this data can be accessed using next generation sequencing device. But the problem is, due to the current technology that we have for next generation sequencing, it incurs some 12 to 18% of error, some noise. And this noise are, so essentially what we will see. So instead of getting, I mean, directly look into, I mean, getting this each of the block correctly, we will see some of the noisy copies of them. Okay, so when I ask for this whole data, so for each of the part, I will get some noisy copy and they are all intermixed. And this noisy copies, I mean, this noise are essentially the random edit operations. Okay, so now let's see pictorially. So these are the data that I want to retrieve back from the DNA storage system. But essentially what I get is some of the noisy copies. So for example, so for this yellow copies, I get so maybe 3 noisy copies of this yellow, and then red, purple, and green. So now the question is, how do I get back the original data? Because if I could not get back the original data, so then is no point of using this DNA storage system. And these are the computational problems that arise, and I think they are also nice from the theoretical point of view. Oh, so what is the first step? So first step to get back, retrieve back this actual data is clustering, because all these things are intermixed. So now I will cluster them so that at least I can identify that from which set of copies I should get the actual copy. Okay, so now I cluster them. So all the yellow points will come into the cluster 1, then red points in the cluster 2, and so on. So this is the first step, clustering. And once I get the, I mean, do this clustering, so after that, my next task will be to get back the original data. So from this cluster 1, which are essentially the noisy copies of this YOLO file set, I mean YOLO block, I should get the exact original data. Okay, so this is the second part. So, and that's how, I mean, now you can see, I mean, why I mentioned this clustering problem. So this is the first part is essentially that given a set of files, I want to partition them according to the similarity between them. And we want efficient procedure. And of course, now so here we have to talk about the running time of the clustering algorithm, what are the accuracy, and so on. But unfortunately, we don't know much non-trivial result for clustering when the underlying distance measure is the edit distance. I mean, there are some of the clustering algorithms that works for general metric spaces. Only those are known for, I mean, those will also hold for edit distance, but nothing special is known. For Hamming distance, there are several non-trivial work, but such techniques won't extend directly to the edit distance. So there is one work on clustering for this type of noisy data that actually appear in this DNA storage application. So that appears in NewLib 17. But they have some theoretical guarantee and also empirical result, but that also could not really solve the actual problem. And this result only work, I mean, for this special type of data, like when there are some of the noisy copies. So what are the objective here? So here the objective is that I want a much faster algorithm than n squared. So here n is, you can think of like the original data size. Okay, so and why somehow I want to beat n squared here? Because if you think of like, so if the original data is of size n, so then even if I divide them into constant size block, so there will be at most theta n block. And since these are noisy copies, maybe just by computing edit distance between all the pair of these noisy copies, I can be able to cluster them with sufficiently large probability. Okay, so yeah, so this is the clustering problem. But this is again not really the topic of this talk. I will not go into the details because we don't know much about this problem. But I just wanted to introduce you to this problem because this is like the first part of the DNA storage system. So what we will be mostly focusing on in today's and tomorrow's talk is the second part of the this application. So as I mentioned that after clustering, so the second step is to get back the original data from the cluster. So now from now on, what we will consider that suppose we have an efficient clustering algorithm and we get the cluster. So now even if we get the cluster, how do we reconstruct the original data? Okay. Yeah. So now here is the formal description of the problem. So this problem is referred to as the trace reconstruction problem. So here our objective is to reconstruct an unknown string from its noisy observable copies, and each of these observable copies are also referred to as traces. So there is an unknown string x, so we will use n to denote the length of it. And now the noisy copies are x1, x2, xm. And our objective is to recover x. So you can see that this is exactly the problem that we have seen in this DNA storage application in the second step. So now what are our goals? First of all, we want to use as few samples as possible. Second, we want to minimize the error while recovering this unknown string. And third, of course, we want efficient algorithm. Okay. And this problem actually has been studied a lot. So there is a huge line of work which consider this trace reconstruction problem under different noise models. Okay. So here is, suppose this is our x. So I don't know why the first part is colored as blue. So actually, yeah, so there is nothing special here. Anyway, so this original string x is passed through the noise channel, and I get one noisy copies xi. So there are different noise channels that people consider in the literature. So one of the most simplest model is the substitution model, where each symbol is flipped with probability p. And somehow this model is slightly easier to handle. I mean, like a reconstruction of the original, the unknown string, when the underlying model is the substitution channel, is pretty simple. Now, the more challenging one is the deletion channel, where each symbol is deleted with probability. And even more challenging one is the insertion deletion channel, where you delete some character with probability p by 2. You can also insert some randomly chosen symbol with probability p by 2. And with remaining probability, maybe you can keep the symbol as it is. Okay. And well, so this is not really the most general model, because I mean, most general probabilistic model, because in some of the applications, these probabilities could be different. Maybe with P1 probability, you delete, with P2 probability, you insert, and there could be also some probability of substitution. But essentially, generally, whatever be the result that work for this type of simple insertion deletion model with the same deletion and insertion priority, they generally extend easily to this most general model. And now you can see that this channel is exactly what we have encountered in the DNA storage application, because there, when we have seen this next generation sequencing step generate these noisy copies, those noises are this type of random insertion deletion noise. So then if you can solve the trace reconstruction problem in this particular model, then it will also give us efficient way to get back this stored information in this DNA storage system. Okay, so we will consider this insertion deletion channel. Okay, so any questions so far? Yeah, please feel free to stop me anywhere and just ask me question if you have anything.
So our current target is, given this X size, we have to generate the X, right?
Yes.
Okay, okay.
And is the number of samples somehow, I mean, do we get to control that, or is it a function of the error probabilities somehow?
Yes, so it will be some function of error probability.
Right, okay.
Yeah,
Thanks.
because I mean, like if you see say 1 or 2 samples, maybe it is unlikely that we'll be able to reconstruct.
Correct, correct, makes sense.
Oh, so in the literature, so there are two cases that people consider with respect to the unknown string. So the first case is like the most general one, worst case. So like unknown string is arbitrary. So although the random noise channel is probabilistic, but the unknown string is arbitrary. And in the another case, the unknown string is an uniformly randomly chosen string. So this is the average case model. And some of you might wonder, I mean, is it just for sake of simplicity, sake of fun, or what? I mean, maybe, sorry, okay. Maybe you may wonder that maybe I just want to solve worst case version, but I cannot solve it, and that's why I just tweak it to first solve the average case. So this is not exactly the case, because even the average case version has application, like just now the DNA storage application that I mentioned, that is essentially the average case, because if you recall that I mentioned that in the pre-processing step, somehow I randomize the stored data. So that's why whatever the data being stored is almost like a random looking string. Although it is not exactly random looking because of application of some of the error correcting code there, but this is roughly random looking. So that's why you can think of like, if you can get a good algorithm for this average case version, that we should be able to apply in this DNA storage application. Oh, so now what is known? Because I mentioned that already there is a long line of work on it. So in the worst case version, so first of all, okay, so whatever be the this long line of work that I mentioned, so all of them actually consider the exact reconstruction. Okay, so I want to basically they consider this unknown string to be reconstructed exactly. So not even a single error there. And for that version, I mean, like exact reconstruction, the current upper bound for worst case is like exponential. So it is 2 to the n to the 1/5 traces are needed. And on the other hand, the lower bound is like only polynomial into the 3/2. So there is this huge gap. And even the similar thing is true for average case. I mean, this exponential gap is still there. So in the average case, the upper bound is much better than this exponential one. So it is now exponential, but not in n, but rather log. So it is e to the log n to the 1/3. And so this is sub-polynomial traces. And the running time is also almost linear. And it is known that you need log to the 5 by 2n traces to reconstruct them exactly. And again, you can see that there is a huge gap between the current upper and the lower bound. Okay. But what about approximation? Because all of these are for exact trace reconstruction. But maybe for many applications, we don't need exact trace reconstruction. For example, this our favorite DNA storage system application. Since we use error correcting code in the beginning, maybe even if we could reconstruct up to certain error, then it is fine. So that's why it suffices to recover a string Z that is close to the unknown string X. It should not be like exactly equal to X. And edit distance is a natural closeness measure when I consider this closeness between the reconstructed string Z and the unknown string X. And why it is natural? Because our this noise is also like edit noise. So that's why the edit distance, I guess, is a natural choice. Okay. So what we can do trivially, what we can argue trivially here? Well, so if you could just output one of the input trace, so that is also close to edit distance in the sense that up to this PN edit error. Okay. Because since I mentioned earlier that we delete with probability p by 2 and insert with probability p by 2. So essentially with probability p, I am introducing a noise. So roughly then the edit distance will be at most Pn. And so that's why, I mean, if I just output one of the input trace, this is Pn close. I mean, up to the distance Pn. Okay. So the question is, can we do better? Can we get show some non-trivial result here, which is like smaller than Pn? So the answer is yes, and we will see that proof tomorrow, that how we will get something better than Pn. Okay. And now let me go to slightly different problem. So is there any question so far on the trace reconstruction problem? Like on the problem formulation, previous work, anything?
No, it looks like we're all good here. Yeah.
Okay. So again, so recall, so this was our application, and in the step 2, essentially we were solving the trace reconstruction problem. Okay. So now you can see that whatever I have mentioned so far are for exact reconstruction, and those algorithms are not really practical. I mean, for average case, there are near linear time algorithm I mentioned, but those are not people use in practice. But rather, what people use in practice is some kind of heuristic. So what they do is like they find some kind of representative. Okay, so instead of this, I mean, this is what the unknown string is, and that is what I want to recover. And I am given only this noisy traces. So what people do, they use some heuristic to find a representative. And they just believe that most likely that representative should be same as this unknown one. And one of the representative, I mean, one of the way to define representative is a string that minimizes the sum of distances. Okay. And that defines the notion of median. So here is the problem statement. So given a set of strings, x1 up to xm, so the objective is to find another string y from the ambient space. Okay. So here are basically our given string. x1, x2, x3, x4, x5, x6, and so on. And what I want to find some string which need not be same as one of these input, but it could be somewhere here, some y, such that it minimizes the sum of distances. It minimizes the sum of distances from each of the input strings. Okay, so this sum of the distances is our objective value, and that is what we want to minimize. And suppose y star be a string that minimizes this objective value, so then we call y star a median. Okay, so although I define everything in terms of the edit distance, but there is nothing specific here. So the median is a very classical data aggregation problem, and that is defined for, one can define for any metric spaces, and that actually being studied for other, like geometric spaces like Euclidean space, and also like Hamming distance, Jaccard similarity, rankings, and so on. And depending on this underlying metric space, this median problem has numerous applications. But I will not go into there. So throughout this talk, I will only restrict ourselves to the median problem where the underlying distance is the edit distance. Okay. So one question is, how do I find median string? Because I already mentioned that in practice, to solve the trace reconstruction problem, people use heuristic to basically solve the median problem. So actually, this problem is also turns out to be very difficult. So it is shown to be NP hard. But there is a dynamic programming algorithm, which is essentially some kind of extension of the dynamic programming algorithm that we have learned, which compute the edit distance between two strings. One can actually extend that dynamic programming algorithm and get a median string algorithm. But the running time is now exponential. So essentially, the running time is 2 to the m times n to the m. So m is the number of input strings, and each of the input string is of length n. Okay. So, and that is why I was also saying that this is a extension of this two string case, like when we find the edit distance, because they are essentially m is 2, and that's why we were getting n square. And now, since instead of two string, I have m string, somehow I am getting n to the m running time. And unfortunately, it is also known that under this assumption of ACTH, we cannot get much better than this running time. Okay. So now again, the question is, can we do something better with the help of approximation? So what is approximate median? So already in our first talk, Arindam already introduced us to the definition of approximation algorithm. And I guess anyway, I guess most of us already know about it, but just to make sure that we are in the same page. So here is the definition. So suppose the optimum objective value that is attained by a median string, I denote by opt. Okay. So then I will say a string y bar is a C approximate median if the objective value, when defined with respect to this y bar, so which is, if you recall, our objective value was the sum of edit distance from x to y bar. So x is all the strings in the input set. So which is at most C times opt. So then we will call this y bar approximate C approximate median. Okay. So now you may wonder, why I am suddenly now defining this approximate median. So is there any real connection between approximate trace reconstruction problem and the approximate median? I mean, I have mentioned that in practice, people use this heuristic to solve this trace reconstruction problem using median. But we have already seen that median is already NP hard. So basically there people use two types of heuristic. The first heuristic is like to solve trace reconstruction, solve median. And then even to solve median, they use another heuristic. Okay. Okay. So, but now the question is, can we prove something theoretically? So, yeah. So some algorithm that have theoretical guarantee. And also I want to just introduce to you this term multi-sequence alignment, because some of you might encounter this term. So this multi-sequence alignment is nothing but whatever I just defined, this median with respect to edit distance. I mean, multi-sequence alignment actually has different version, but one of the popular version is essentially the rephrasing of the median problem with respect to edit distance. Okay. So one of the concrete question to think maybe that what is the, I mean, is there a definite connection between these two problems? Can we show something theoretically? Okay, so maybe you can think about this problem today, and I will come back to this tomorrow. Okay, so what are the questions we encountered so far? So first, I ask you the question that how do we cluster a set of text with respect to edit distance? And the second question was how to perform approximate trace reconstruction efficiently. If you recall, so this was essentially our step 1 in the DNS storage application, and this was our step 2. And that is how we get to see these two problems. And then the third question was, what is the connection between approximate trace reconstruction and approximate median? And then the fourth question is, how do we find approximate median efficiently? So far we have seen this 4 questions. And I also mentioned that this first question we will not talk about today or tomorrow. Okay, so essentially what we will be seeing from now on is try to answering these 3 questions. Okay, so maybe let's take a pause for a few seconds, and if any of you have any questions so far on this problem formulation, you can ask me.
So I guess this is super high level, but is the hope that you can treat the noisy samples as strings in such a way that the closest string may somehow be a decent approximation to the word that you're looking for? Is that the kind of thing that you might be able?
Yes, that is where I am approaching. So basically, I want to solve this trace reconstruction, and now first I want to show that if I could find this approximate median, that will be give us some approximate trace reconstruction, and that you suggested, and then I will solve the approximate median problem. And now as a combination of these two, I will get a good answer to this second question, that is, we will get a good trace reconstruction.
Okay, that's very cool.
Okay.
Yeah. And the other question is probably out of scope, but are rankings going to come up now?
Yes.
Okay.
I think you are right. I mean, because so far we have not seen rankings anywhere. Soon it will come up. Okay, so before going into the rankings, what is approximate? I mean, we have defined approximate median. So now one trivial question, I mean, as I mentioned in the last slide, the fourth question was how to find an approximate median efficiently. But can we get a constant factor approximation in polytype? I mean, we know that it is NP hard. So the question is, can we get a constant factor approximation? Any large constant for now will should suffice. So I want to claim that 2 approximation is easy. So the question is why? So some of you might have already seen this, but those who are not, maybe you can try to make some attempt. I mean, here we are not asking for like super efficient algorithm, just polytime algorithm should be fine, as long as it gives us 2 approximation guarantee. So then let me suggest. So one of the easiest way is like output the best input. If you recall, so when I define the median problem, I say that we are given all these input point, x1, x2, x3, say x4, x5, x6. And now I am asking you to find something which may not belong to this input set, which could be some arbitrary point from the ambient space. So that could be your actual median. But now I am saying that instead of that, if you just output the best input, so something from just from this input set, which minimizes this quantity, this objective value. So if you again recall what was the objective value, it was sum of distances. So now I am saying that whatever be the best input, that should give 2 approximation. Why? This is just because the application of the triangle inequality. So let's try to see it. I mean, it is not difficult. It is pretty simple. So let's consider the closest point to this. I mean, there is this unknown actual median. Okay, so y star. And so consider the whatever be the closest point among this input set is. Suppose this is z. Okay. So now, what is this objective value? So the objective value is summation x to c, x is from s. And now I use the triangle inequality, and which enables us to write this in the following form: edit distance from z to y star plus y star to x. Okay. And now what I consider? So this is the closest to this unknown y star. So then I know that this quantity is definitely smaller than equal to this quantity, right? Because just by the definition of closest, so I know that for all x in S, the edit distance of z to y star is at most edit distance of x to y star for all x. So that's why now I can replace this quantity by twice y star to x. So which is twice y star to x, and this is essentially the objective value with respect to y star, and since y star we consider as the unknown median, so this is essentially our opt. So then you can easily see that now we get the 2 approximation. Okay. So now since this whatever be the closest to y star is giving us 2 approximation, then now if we minimize over the set of all strings in the input, definitely we'll get something better than that. So that's why the best input will give us 2 approximation. And another interesting thing is that there is nowhere I use the fact that it is edit distance. So only thing we used is that it follows the triangle inequality. So that's why this argument holds for any metric space. So for any metric space, essentially, if you output the best input, it will give you 2 approximation for the median problem. Okay. So now, yeah, so is this argument clear? And I think this is a pretty simple argument, and I guess most of you have already seen this argument before. So yeah, so this holds for any metric. So now the question is that for edit metric, can we prove something better? So what about say Peters, or like even breaking below 2? Can we get something say even like 1.9? Can I get 1.9 approximation when the underlying metric is edit distance? So this is the question we want to solve from now on. Okay. So now let's take a special case. So the Hamming distance. So Hamming distance is a special case of edit distance because for edit distance, the set of edit operations are insertion, deletion, substitution. On the other hand, for Hamming, we only have substitution. So it turns out the median problem for Hamming distance is very simple. Why? So suppose these are our input strings and I want to compute the median. So now let's look into one column, okay? So suppose, okay, so forget about everything. So suppose you are given only this data 1, 0, 0, 0. So these are 4 data points. What is the median? Yeah, so median is 0. So essentially, if you take the majority, so that will give you the a median. Okay, and this argument extends for the whole string because the Hamming distance is essentially coordinate-wise dissimilarity, right? So then you can essentially solve it like coordinate-wise separately. So essentially, output the coordinate-wise majority. And if there are some ties, like if for some coordinate like half or 1, half or 0, you can just break ties arbitrarily. So for this example, so the y star could be just like for the first, the majority is 1, then the second, the majority is 0, and so on. And it is not difficult to show that this will give you the median. I mean, of course, I am not saying the median for Hamming is unique in the sense that since I am breaking ties arbitrarily, so for the columns, oops. Anyway. Okay, so suppose I look into this particular column, you can see that there are exactly 2 1s and 2 zeros. So we have 2 choices. So no matter what you, whether you choose 1 or 0, both will lead to a median. So that's why medians are not unique, but it is very easy to compute. I mean, you can find one median with this algorithm. But that is not the case for edit. Okay. So this is one special case. And now comes the ranking part. So what about the permutation? So this should be another special case. So what do I mean by permutation? So you can treat the permutation of 1 to n as a string. So essentially, instead of considering arbitrary n-length string, consider the permutation. And now just the distance measure, you consider the edit distance. Okay. So what is the edit distance between two permutation? So the minimum number of insertion and deletion. Exactly same as how we define normal edit distance. But just don't consider the substitution operation, only because I have to make sure that both the, I mean, after applying these edit operations, I should also go to a permutation. So that's why let's restrict ourselves to insertion and deletion. So for example, I mean, suppose these two are two permutation on from 1 to 9. And now what is the distance? So maybe the edit operation is like I will delete 8 and also I will delete 2. And then I will place 2 here and 8 here. Okay. And then you can see that I will get x2. So the edit distance is then 4 because 2 insertion and 2 deletion. And this may, I mean, this also has a special name. I mean, like set of permutation where the underlying distance is edit distance. This is referred to as the Ulam metric. Okay. So the distance wise, this is really a special case of the normal edit distance. But when I consider the median problem, is it really a special case? So what is the median problem when the underlying space is Ulam? So again, we are given a set of permutation, which are essentially n-length strings. The objective is to find a permutation Y, and again, not necessarily from S, such that this minimizes sum of distances. And now you can see that this is not really a special case. Why? Because now I am asking to output a permutation. So when it is defined over string, so then the output could be an arbitrary string. But here we have a extra restriction that the output has to be permutation. So that's why the median defined over permutation is really not a special case of the edit median, although the Ulam metric is a special case of the edit distance. Okay. So then why do we consider Ulam median? First of all, it captures several inherent difficulties of edit metric. I mean, it is true for when even we consider two strings as well. It turns out like, I mean, there is a huge literature on computing edit distance between two strings. And it turns out that when the input strings are permutation, then somehow it is easier to compute. And but there are some of the similarity in terms of difficulties. So one can actually get some of the ideas from those Ulam distance finding algorithm to get a efficient edit distance algorithm. So this is one motivation. And another motivation is like permutation you can view as rankings. And Ulam distance is just an interesting dissimilarity measure among the rankings. So why these are rankings? So now suppose there are 6 positions in some institute, and these are like hierarchical position. Okay, so this is like the topmost position, this is the second topmost, and so on. And there are 6 candidates. And now there are people who actually vote or rank them. So maybe the voter 1 ranked the 6 candidate in this way. So 1, 6, 5, 3, 4, 2. Then the voter 2, 2, 1, 5, 3, 4, 6. And now what is the problem here is that all those voters give their own ranking preferences. And now you have to aggregate them so that it will minimize the sum of distances to all these voters' preference. So for example, so here, suppose I aggregate all the ranking, I get this particular ranking. Now you can see that this particular ranking is of distance 2 from each of the voter ranking. So for example, so suppose this is my final aggregated rank. So now you can see that for voter 1, essentially I need to delete 6 and I have to place 6 here, and then I will get final ranking. So for voter 3 also, I have to delete 1 here and put it here. And that's why the edit distance, I mean, or the Ulam distance, I mean, so generally edit distance over permutation is considered Ulam distance. So this is just 2 for each of them. So now the objective value wise, what is the objective value? It is essentially 8. And I guess you can show that this is the optimal for this example. And this particular problem has, again, several applications, starting from social choice theory, sports, database, statistics, internet, and so on. And we want to solve them. So I guess I am almost out of time. So maybe within 1 and 2 minutes, I will end this talk, and I will just keep the remaining for the tomorrow's. Okay, so this is our rank aggregation problem. And as I mentioned, the Ulam distance is just one of the dissimilarity measure among ranking and permutation. So there are actually several other popular measures that are used to compute the dissimilarity between rankings. For example, Kendall-Tau, with respect to which this rank aggregation is also called Kemeny optimal rank aggregation, Spearman-Foote rule, Kelly, Minkowski, and many more. And each of them has different applications. So one of the interesting one, maybe this is like the most popular one, so that's why I just emphasize that, this Kendall-Tau, which counts the number of inversion. So don't have to go into the definition for this, because we will not see any result for Kendall-Tau, or at least we will not explain any result here. So I just want to emphasize this particular Kendall-Tau measure, because this is perhaps the most popular dissimilarity measure among rankings. And under this measure, I mean, people have considered the rank aggregation or median problem. And it turns out, again, there is a huge literature, and it turns out that this is NP hard with respect to Kendall-Tau. And even for 4 input, like even if you are given 4 ranking and asked to find the median, so that problem is NP hard. But on the other hand, there is a PTAS. So essentially, there is a 1 plus epsilon approximation algorithm in polytime. But for 3 inputs, we don't know. So this is the story for Kendall-Tau. And now what about Ulam? Because this is what now we are interested in. So unfortunately, we don't know for Ulam it is NP hard or not. I believe that it should be NP hard, but I don't know the proof. So you are welcome to come up with some proof. And what we show very recently is that we can get 2 minus epsilon approximation. And just unlike Kendall-Tau for 3 inputs, for Kendall-Tau, we don't know for 3 input whether it is NP hard or P. But for Ulam, we can show that it is NP. Okay, so that is like the story so far for the rankings. Okay, so from so I will end here, and from tomorrow I will start from here actually. So I will show you how to basically prove these 2 results, and how this idea from Ulam, I mean, whether that will help us in getting solving the approximate median problem for the more general edit space. And then I will establish a connection with the trace reconstruction, and finally derive result for trace reconstruction. Yeah, so those remains for the tomorrow's talk. Okay, so yeah, let me end here, and if now you have any question, you can ask me.
Yeah, thank you so much, Diptarka, for that wonderful talk. So on behalf of everybody attending, I think an applause at this point. So tomorrow's talk will be in reverse sequence.
Yes, it will be in the reverse sequence. Now we will see the solutions. So we'll start with the solution of Ulam, then go to the edit, then connection with trace reconstruction, and so on.
Right, that's Yeah, I think that's going to be really interesting. So just a quick sanity check. The Kendall tau distance can be quadratic, right? It can be as bad as n squared between two permutations over
n choose 2,
matrix.
yeah.
Right. And
on
but
the other hand, for Ulam, it is just order n.
Order. Right. Yeah, it's also interesting because, I mean, I guess if you had two voters, for instance, let's say one of them votes 1 through n and the other voter puts the first candidate at the end, versus another voter just swaps the first two candidates, then in both cases, the Ulam distance will be just 2, right? So the distance doesn't distinguish between what looks like a minor change and what looks like a major
change. Yeah, so it will not, so that's why these two distances are not directly comparable that way.
Yeah, that's interesting. It's also interesting that the hardness of median is unknown as well. Okay, it feels like one of those things that should be hard, but I guess it's right.
So actually, so there is, so maybe I will mention that tomorrow. So I mean, there is also another way of measuring this rank aggregation, or like any data aggregation is like mean max. So today I talked about mean sum. So now if you minimize the maximum, so that is called center. So with respect to that, for all of this metric, N delta, Ulam, everything actually known to be NP hard. But that is not true for median, at least.
Right.
We don't know this.
Right. You minimizing the worst distance. Correct. Yeah. That's right.
Yeah, that should be more difficult than the minimizing the sum.
Correct. So Anirban, go ahead.
Yeah. So I mean that's very interesting because we had come up on in our class that we sort of have that we discuss distance functions beginning of data science thing. We had come up on this thing about that what other properties would be nice to have this, right? And at one of the discussions we came up on this property that it would be nice if we can calculate sort of medians easily. Do you know for other distance functions, like you mentioned somewhere the Jacquard distance, right? It doesn't seem obvious to me for that too, but do you know what the results?
I think Pitas is known.
Oh, for Jacquard, Pitas is known. Okay. Oh, cool. That's interesting.
I think for Jacquard, like both the median and center, I think Pitas is known. I think so, if I recall correctly.
So are there any other questions? Feel free to unmute yourselves if you'd like to. I don't see any questions in the chat.
So today's talk was so simple, so that's why there is no question. So maybe tomorrow we'll have lots of questions.
Sure. Yeah. I think you have asked all the questions at this point, and you've stopped at a nice cliffhanger. So I'm sure we are looking forward to your follow-up talk. And if anybody had questions that they couldn't get in today, tomorrow would be a great time to ask as well. So thanks so much again, Deeptarka, and to everybody who joined. It's back to the organizers, as I think we are getting ready to call it a day. So thanks.